Hello, good afternoon, everyone. I hope you had a good weekend. Let's get started. So, last class we were talking about scientific method, and we look at discovery science as a way of conducting the scientific process. In discovery science, you are making observations without changing the system. You're not introducing any kind of alterations to what you're observing, and when you are making observations, you can either observe using your senses, so seeing things, touching things, tasting it, smelling it, or even using sound. These kind of observations are called qualitative observations. They do not involve any numbers, and you are just going to be basing the observation using your own senses. Because you are using your senses, though, the observation can be a little bit subjective. It depends on who's making the observations. Different people might have different definition of you know rough texture. Okay, what feels rough to one person might not feel as rough to another person, and so qualitative observation, while they're easy to make, it's often a little bit subjective. So to make things a little bit more accurate, we sometimes would use quantitative observations. These are observations that are made using instruments. It involves numbers, and so that those tends to be a little bit less subjective. If you and I use the same instrument and we are both using it correctly, then we should arrive at the same measurements. Okay. We also talk about how you can go from specific observations to a broad generalization. This kind of logic is called inductive reasoning, and you can apply the generalization to other specific cases. And in that regard, it is called deductive reasoning. Okay, so that's where we left off. And we're going to spend much of today talking about the second scientific approach, which is called the hypothesis driven um, science. Okay, so let's go to the PowerPoint and see what it is. So here are the steps that are involved in the scientific method. It involves making observations, asking questions about what you are observing, and then coming up with a hypothesis, predicting the results, performing an experiment, and then arriving at a conclusion. We will be looking at different case studies throughout today's class and see how these different steps would be like in different scenarios. As always, if you have questions, feel free to stop me at any time. You can type the question in the chat box, and yeah, I'll answer them. So let's start with uh, an example that we might all be familiar with. Let's say you try to turn on the TV and nothing happened. So that's the observation. The remote doesn't work. The natural question to ask would be, what's wrong with the remote? And then you try to answer your own question. You have some guesses as to why this is the case. So this is the hypothesis stage. Right? You're trying to come up with a tentative answer. And this tentative answer, some people call it an educated guess, is often based on your previous experience. Maybe this happened to you before, right? And last time it happened, I changed the battery and it was fine. So the batteries are probably dead. Right? So you make a prediction. If I'm right, replacing it with new battery is going to fix the problem. You then go ahead and do the experiment, which involves replacing the batteries, and it either fixes the problem, the remote works now, right? Which means your prediction was correct, your hypothesis was correct. Or if the new batteries do not fix the problem, then the experiment does not support the hypothesis. And then you got to come up with a new hypothesis. You need to revise the hypothesis. Maybe it's not the battery. Maybe the TV is not plugged in or something, right? So there are other possibilities that could lead to this situation, right? And then you kind of try different things until you solve the problem. Right? So this is, of course, an oversimplification of how the scientific process work, but nevertheless, it should help you relate to your own experience. So let's say we look at another scenario. Right? We see that some plants grow taller than other plants. You have two pots of plants at home. One is taller than the other, and the natural question to ask would be, why does one plant grow taller than the other? Okay. So after asking the question, the next step would be to formulate a hypothesis to come up with a tentative answer. So help me out here. Why do you think one plant grows taller than the other? What might be some contributing factors? Okay. Omar said soil. So maybe one plant has better soil than the other. Kyle said the environment. Yeah. Would you like to elaborate on that a little bit? Like, what about the environment? Okay. Alpha says the sunlight, right? Water intake. Yeah. So there's so many different things that could be the problem, right? There could be so many things that's causing it to be different height. And so we try to pick one thing to look at a time, right? Because as you will see, you cannot test multiple things in a single experiment, right? We'll keep that in mind as we go forward. But these are excellent suggestions. So let's define what a hypothesis is. A hypothesis is, you can think of it as a tentative answer. Tentative answer to the question that we're asking. And in this plan scenario, we are trying to figure out why one plant is taller than the other. So your hypothesis could be one plant is taller than the other because it receives more sunlight. Okay. Now, hypothesis in the context of the scientific method needs to be written in a certain way for it to be meaningful, for it to be valid. Right? Number one, the hypothesis must be testable. You must be able to conduct an experiment to test the hypothesis. Okay? Testable means can be tested in an experiment. If you can't test it, then it's not a good hypothesis. Number two, it must be falsifiable. Falsifiable means it can be potentially false. Okay, like your hypothesis must be, there must be a chance that it's wrong. If it's always correct, then you didn't need to ask the question already, right? If you know the answer to the question and you come up with a hypothesis that's always correct, then what's the point of asking the question in the first place, right? Now, things that are that should not be included in a hypothesis include these things. I'll just read some of them. Okay, opinions, religious beliefs, moral judgments, supernatural stuff. These things should not be part of a hypothesis, okay, because you cannot test them, and in some cases they are not falsifiable. So let me give you a few examples of invalid hypotheses. Okay, hypotheses is just the plural for hypothesis. Number one, animal testing is bad. Right? Rock music are better than classical music. Why are these invalid hypotheses? What's wrong with them? Anybody? No facts is supported, opinion, subjective. Yeah, these are opinions. These are subjective. Okay, you cannot prove a person's opinion to be correct or incorrect, right? And furthermore, these are not testable. You cannot test a person's opinion, right? So that's why they are invalid hypotheses. The garden fairies made some plants taller than others. Everything that everything that occurs is as a result of divine intervention. What's wrong with these hypotheses? Why are they invalid?
They are
Okay.
based on religion.
Yeah, they are religious beliefs. They are personal opinions, or not really personal opinions, but like things that people believe, right? Well, we cannot say it's false, right? That's the problem, Regipen. Like we cannot prove it to be false, right? How do we know that there is no divine intervention? Okay, how do we know there are no garden fairies? Okay, like you might laugh at it, right? Like, of course, garden fairies are not real. But here's the thing, right? How do you show that they don't exist? You can stay in the garden and observe for a whole month or 2 months or even a year, and you don't see any garden fairies. And then you say, "Oh, garden fairies don't exist." But then someone can say to you, "Well, just because you haven't seen it doesn't mean they don't exist, right? You just haven't waited long enough. If you wait longer, right, you will be able to see it." Right? In fact, you can spend your whole life looking at the garden and not see one, and the counter argument will still be, well, you just haven't seen it because you weren't lucky enough to see it. Like, it doesn't mean they don't exist. So for that reason, these last two examples are not falsifiable. All right, you cannot prove them to be wrong. And if you cannot prove something, if you cannot show something to be wrong, then it's not a valid hypothesis. Okay, so testable and falsifiable. Those are the two conditions that must be met in order for a hypothesis to be valid. Does anybody have any question about this before we move on? All right, let's take a look at some valid hypotheses. Plants receiving more sunlight grows taller. That's something we can test. We can put plants in sunlight and then not as much sunlight and then compare the results afterwards. It's falsifiable because if they end up to be the same height, then we know it's not the sunlight that's causing the difference, right? Here's another one. Driving with the windows down will increase fuel consumption. Some people believe this is true because if you have the windows down, all the winds coming in increases resistance, and therefore you use more fuel. Other beliefs is better for the fuel consumption because you're not turning on your heat or your AC, right? So that's something you can test, and something that's potentially wrong. Another good hypothesis would be taking melatonin will increase sleep duration. Does anybody know what melatonin is? Have you heard of melatonin? Where can you find it? Yeah, where can you find it, Annabelle? Do you know? Or anyone else? Your body actually makes melatonin for you. It makes it in the brain, and it's supposed to help you sleep. Okay, but people can also buy melatonin from pretty much anywhere. You can buy it at Walmart, and people who take melatonin pills say they sleep better. Right. So some people believe it. Others actually think it's a placebo. Placebo is like a psychological effect, as you will see later on in today's lecture. So regardless, that's something that you can test. So therefore, it's a good hypothesis. All right. Once you have a hypothesis, you need to design an experiment to test the hypothesis. Okay. Anyone can have a hypothesis. Okay. Like back to our plan example, right? You might think it's sunlight. Someone else might think it's soil. Someone else might say it's water. Okay. And then, it could be a collection of those things. But you can't say, you're right or you're wrong without doing an experiment. Okay. In order to figure out who's right, who's wrong, and which factor affects the height of the plant, you must go on and do the experiment. And so when you do the experiment, there are things that you are supposed to change, and then there are things that you're supposed to not change, right? And it depends on what kind of experiment you're doing. the things that you're changing would be different. So something that you can change in an experiment is called a variable. A variable. Right? Now, there are different kinds of variable: dependent variable, independent variable, and there's something called like standardized variable. So let's start with dependent and independent variable. Please take out some paper. We're actually gonna be taking quite a bit of notes today. Okay, I'm gonna have at least like 2 pages of notes. So here we go. Let's talk about independent variable. Independent variable. So in an experiment, I just want to make sure that you guys can see my screen here. Yep. Okay, so independent variable. This is the variable that is changed deliberately in an experiment. Right? The independent variable is the variable that you change on purpose in an experiment. You can try to remember this by seeing the word independent variable is the variable that you are in control of. You have to say that I want to change this or not. Okay, so that is the independent variable. So in our PowerPoint slide, I'm gonna come back to this later. Okay, if you haven't finished copying everything, let's take a look at here. All right. Let's say we want to do an experiment that check the first hypothesis, that test the first hypothesis. So what would be the independent variable in this experiment? You cannot control how tall the plant grows, but you can control the amount of sunlight that you give to the plant, right? So the independent variable would be the amount of sunlight. Is it 6 hours of sunlight? Is it 12 hours of sunlight? Is it 18 hours of sunlight? How much sunlight you give to the plant, you are in full control of that. That would be the independent variable. Let's say we do an experiment to test the second hypothesis. Driving with the windows down will increase fuel consumption. What would be the independent variable in the second case? What is the independent variable? I'm sorry, what was that?
The windows being
Yeah,
fully shut
this
down
the
or with windows being open. Yeah. So
exactly right. It would be the position of the window. Position of the windows. Do you open them? Do you close them? Okay. Position of the windows. That's you can control. You can open them or you can close them. You cannot control the fuel consumption. Okay. How about the last one? What would be the independent variable if we were to do an experiment to test the last hypothesis?
Maybe how much sleep you get?
Okay, now is that something that you can control though? Like if you have groups of people in this experiment, like can you control how much they sleep?
Maybe like a alarm or some sort.
Okay, I see what you mean. Yeah, okay. Um Afra, I'm sorry if I'm pronouncing this wrong, okay? But yeah, amount of melatonin, that would be correct. Okay. So the independent variable here would be amount of melatonin. You can control who takes what. Okay, like let's say you set up different groups. Okay, this group you give no melatonin, this group you give melatonin, right? that you can control. But like how long they sleep, like sure, I understand your point of like putting an alarm there to wake them up, but you know, like but like we can't really control how long they sleep in general, right? Like they sleep for 8 hours, 6 hours, right? That's like not something we can control, not to the degree that we can control, you know, whether to give them the melatonin or not, right? So in that case, the independent variable would be the amount of melatonin. Does anybody have any question about independent variable? All right. So the dependent variable would be the variable that is being observed or measured in an experiment. Okay. This is the outcome that you are looking at. Okay. So after we change the amount of sunlight exposure, what you're trying to observe is the height of the plant. The height of the plant would be the dependent variable. After you drive with either the windows closed or open, you are trying to observe, you're trying to measure the fuel consumption. After you give people melatonin or not, you're trying to see whether they sleep longer or not. Right? So sleeping longer or not, that would be the dependent variable. So in an experiment, the goal is to determine, is to find out whether or not, sorry, let's just keep it simple, is to determine if changes in the independent variable will result in changes in the dependent variable. That's the purpose of each experiment. So if changing the, you want to find out if changing the amount of sunlight will affect the height of the plant. You want to know if changing the position of the window, open or close, will change the fuel consumption. You want to know whether taking melatonin or not will change the sleep duration. Right? You want to find out if there is a relationship between the independent variable and the dependent variable. Okay. Now, sometimes the result can be quantified. You can measure it using numbers, and in those cases, we can plot our results. If you're plotting it, then it's important to remember the dependent variable goes on the vertical axis. Okay, this is called the y-axis. And then the x-axis, that's where the independent variable will go. You will learn more about this in your math class, and I think computer course will teach you how to plot data as well. For your first lab, you need to plot some numbers for me. Okay, so remember, dependent variable goes on the y-axis, independent variable goes on the x-axis. Okay, I'm just gonna switch to the study guide briefly. And this is page 2 of the study guide. There are a few examples here. Why don't you guys take a look at the first 2 examples here and try to figure out which one is the dependent, which one is the independent variable. I'm just gonna give you a minute or two to look at that, and then we can take it out. Hey, does anybody want to tell me the independent variable for the first scenario here? What would be something that you would change on purpose? Okay, good
The
try.
students,
Sorry, go ahead.
sorry,
No, go ahead. Go ahead. Yeah.
the student being alone and the student being with others.
Yeah, okay. So like to rephrase that a little bit, it would be watching cartoon alone or with others, right? Okay. Not so much how many people are, or how many people watching with. Okay, I didn't see the with. Okay, yeah, it's like you with others or with by yourself, right? Basically. Okay. And then the rating of how funny they found the cartoon to be, right? That would be the dependent variable, right? How funny. How funny is the cartoon? How about the second one? What would be the independent variable in that case? Okay, Sudima, yeah. Sure, go ahead, Elvis, yeah.
Yes, it's the independent variable to see how the students study the material
Yeah, specifically either
silently or with
exactly. Yeah.
oh yeah,
So the independent variable would be in silence or with TV on, right?
yeah,
Okay. And then the dependent variable would be the comprehension test results.
yeah.
Okay. All right. So I'm just being lazy. I'm just highlighting it instead of copying it. All right. So please work on this yourself later on. Now, when you go to the eCentennial, you will see, go to content and study guide answer. I have to turn them on for you. So there is the answer. Okay, so that's just like the written answers. You can check your stuff yourself. Okay, it's right here. You can compare your answer with it, and for questions you don't know, you can also look at the answers. If you want explanation for the answers, you can click on the tutorial. The tutorial is just like an old recording of me, like taking up this stuff. Okay, so if you need a detailed explanation for certain questions, you can watch them. Okay. Again, content, and then study guide answer. Someone had a question. I saw.
Yeah, it's to see where to find the question itself.
Oh, the question themselves.
Yeah.
You have to go to lecture, and then for lecture 1, study resources. Sorry, not study resources. Lecture notes, rather. Lecture notes, and then here, study guide. Okay, so each lecture comes with a study guide. Does that answer your question?
Yes, thank you.
Okay. All right. Back to our notes here. This card. Give me a second. actually, you guys are 201. I got the session mixed up. Okay, so let's go ahead and do the experiment, right? Virtually. Yeah, go ahead. Do you have a question?
Hi, teacher.
Yeah.
Did you already make the attendance?
Yeah.
Did you already make the attendance?
Oh, I don't take attendance. Yeah, so yeah, don't worry about it.
Ah.
Yeah. Okay, but yeah, glad to have you join us. Okay, so let's say we have two plans here. We're going back to our scenario where we have one plant growing taller than the other, and then we're trying to figure out if it's because of the sunlight. Okay, so no, I would have two plants. One plant here and then another plant here. Okay, so this plan is what we call the control group. Control group. The control group is the group that does not receive any modification. Okay, no changes is applied to it. Okay. And the purpose of having a control group is to provide a reference point, provide a reference or a baseline to compare with. Okay? You need to have the control group in an experiment in order for the results to be interpreted in a meaningful way. For example, For example, if you only have one plant, and then you put it in the sun and then it grew by 20 centimeter, how do you know that's taller than what normally would have happened? Maybe 20 centimeter is how much is supposed to grow anyways, right? Like maybe it's more than it's supposed to grow, maybe it's less than what it's supposed to grow. Like how do you know what normal looks like if you don't include a control to compare with? Okay, so you can think of the control as the normal situation that you can compare other experimental groups with. Okay, so here the other group would be called the treated group, or the experimental group. Okay, for any of you who join later, make sure you go and review the recordings so you don't miss anything. Okay, so the treated or experimental group, this is the experimental group. This is the group that receives modification. Okay, just one modification. You cannot change more than one thing at a time. I'll explain more in a second. Okay. So between the control group and the treated group, okay, I'll say that the only thing that's different between these two groups is what?
Independent variable.
Exactly, is the independent variable. The amount of sunlight in this case. Independent variable. Okay. Everything else needs to be the same. Everything else needs to be standardized. And it's important to make sure you do that, because when you do see a difference in the height of the plant at the end, you want to be able to say with confidence that it was because of the amount of sunlight and not anything else. Right? You only change the sunlight. So if you see one plant taller than the other, it has to be because of the sunlight. If you use different amount of sunlight and then you also use different amount of water, different soil type, and then the plant looks taller, then you really don't know which one was it. Like, was it the sunlight? Was it the soil? Was it a combination of them? You don't know, right? So that's why in an experiment, you only change one thing at a time. Which brings us to standardized variable. And these are the things that you do not change between the groups. I already gave you a few examples. Amount of water. If we are testing for sunlight, then amount of water should be the same. The type of soil should be the same. Can I get a few more, please?
Yeah, the type of plant itself.
Exactly, type of plants. You cannot use different plants. Some plants grow faster than others. If you use lettuce versus, I don't know, spinach or something, they are gonna have different height for sure. What else? Something else? You can type it, you can unmute and talk to me, whatever works. I just
Same
need some
amount of
answers.
sunlight.
Not the same amount of sunlight, right, Omar? Because that's the thing we're trying to test, right? Okay, so everything should be the same, but not the sunlight. Because I want to see if more sunlight will result in a taller plant. Right, but good try. Anything else? Type of pot the plant is in, yeah. Pot size. If you have any plants at home, you probably know the plants are restricted by the size of the pot. Once it reaches certain size, it stays that way until you repot it into a bigger one, right? And then they try to fill up the pot. So that's important to make sure that it's the same pot size. 2 more, please, and then we're gonna move on. What else should be kept the same between the two groups? Temperature, definitely. Yeah, one more. Elvis, go ahead.
Yeah, I was saying the climate, the season.
Oh yeah, okay, yeah. So temperature, yep, good. One more. It's related to the climate. Like, what else did you have to control besides the temperature? Again, not sunlight, right? We want to change the sunlight. Hey, you guys don't understand that. Standardized means the same. We don't want the sunlight to be the same between the control group and the treated group because that's what we are testing, right? Okay, our hypothesis was that more sunlight leads to a taller plant, right? So we cannot keep the sunlight the same. Humidity maybe, right? So all these things are standardized. Okay? And again, in case you missed it, the reason why we need to standardize these things, the reason why we need to keep all of these things the same between the control group and the treated group is so that when you do see a difference in the height at the end, you know it was caused by the different amount of sunlight exposure and not any of these purple things that I've listed. Okay. Questions? All right. So we have the hypothesis, the experiment, right? We would have the 6 hours of sunlight exposure per day. This would be the control standard amount of sunlight. And then this would be the treated group, right? Extra sunlight. You see the two plants are the same. We already listed a bunch of standardized variable here. Initial plant height is also important. Some plants grow really fast at the beginning and then they slow down at the end, right? So like you want them to be at the same height to start with. So while you wait for the results, you can predict the result. What kind of outcome are you expecting if the hypothesis is correct or incorrect? So if the hypothesis is correct, then you would expect a plant that is exposed to more light to be taller. And if the hypothesis is incorrect, then you would expect both plants to be similar height or that the plant exposed to more light will actually be shorter. That's possible. Some plants don't really like too much light exposure. Yeah. So if you give them more light, they might turn out to be shorter. Okay? So both of these outcomes would means our hypothesis is incorrect, and we would have to reject it and come up with a new hypothesis. So let's say we go ahead and do the experiment. You can see with 6 hours of sunlight, the plant grows from 12 centimeters to 13 centimeters, so only a change of 1 centimeter. Whereas if you give it 12 hours of sunlight, the change in height is 6 centimeters. So based on this result, we can conclude that the data supports the hypothesis, and more light will make the plant grow taller. Now I have to emphasize that this is an oversimplification of how science is done. This is actually like if someone were actually to do this in real life and then come to this conclusion, it's actually pretty bad science, okay? Because there are only 2 plants here to compare with, right? You cannot base your conclusion with the result of just 2 plants, okay? When we do an experiment, for the results to be credible and significant, you need to have a large enough sample size. And can you imagine if they're testing a new vaccine, they would have 2 people, okay? One person does not receive the vaccine, the other does. And then let's say, oh, the person received the vaccine, didn't get sick, okay? Conclusion, vaccine works, let's give it to billions of people, right? Like that would be terrible science, right? So we cannot do that in real life. We cannot base the result on just 2 individual plants. But again, like I'm just trying to teach you the basic, right? So that's why we are oversimplifying things. In real life, once you concluded an experiment, it often leads to more questions, and it will start the next experiment. If we find out sunlight will cause a plant to grow taller, maybe another question to ask would be, what is the optimal amount of sunlight? And maybe 12 hours is going to make it taller. Maybe 18 hours will even be taller. Maybe 24 hours will even be better. And then if you figure out 24 hours is the best, then maybe you can change the intensity of the light. Right? You know how the light can be dimmer or brighter, right? So maybe instead of using sunlight, we can use artificial lighting. Some brighter, some dimmer. Is that gonna affect the height of the plant? Right? So there are always more questions that you can test with follow-up experiments. All right, let's do a poll question. See if any of this makes any sense to you guys. There we go. All right, I try to keep the poll under 1 minute. So if you could please choose something, and then we're gonna end the poll. And the polls are anonymous, okay? So feel free to, choose whatever you think is correct. Okay, thank you for those of you who participated. Which of the following step in the scientific method involves producing a tentative answer? We wrote this down earlier. Tentative answer would be a hypothesis. Hypothesis. Let's try one more. All right, any last call? Okay, if you are testing the hypothesis, then you are doing an experiment. Right? The whole point of running an experiment is to see whether your hypothesis is correct or not. Right? So the answer is D. Okay, so we're going to spend the next 15 minutes or so talking about where the concept of scientific method came from, who invented this method, and what was it based on. And then we're going to have a short break. So prior to the mid to late 19th centuries, the origin of microorganisms and decaying matter was in questions. People didn't really understand where microorganisms came from. Okay, microorganisms are like things we cannot see with our naked eye, right? Like bacteria, fungus, those those are examples of microorganisms. So some people supported the idea that microbes arose from other microbes that landed on the food from the air, which, by the way, is the correct answer. But others at the time supported the theory of spontaneous generation. Okay, spontaneous generation states that life arose from non-living matter. It's missing the word generation here. Let me write that in. Okay. So basically, people observe that if you leave a piece of meat outside for some time, and you come back to it like a couple days later, you will see flies and maggots, buzzing around, crawling around on the meat. And people took that as evidence to support the idea of spontaneous generation. Flies, maggots are living things, and they seem to be spawning from the piece of meat, which is non-living. Right? There are other phenomena people were observing that further supported the theory of spontaneous generation. Every now and then, people would see like fish and sometimes even frogs that are raining from the sky. Right? And people were like, okay, fish, frogs, they are living things, and the sky is non-living. Clearly, this supports the idea of spontaneous generation. Now, you might find that ridiculous, but actually it does happen, and it's still happening in modern times. If you do a Google search of like fish raining from the sky or something like that, you will find quite a bit of articles. So Texas witnesses a rare weather phenomena as fish rain from the sky. Happened in Mexico, happened in Australia. So it's actual weather phenomena. Have any of you heard of this before, or is this new to you? I'm curious. Yeah. Some people, okay, some people, frogs. That's right, frogs. Yeah, exactly right. This might be new to you, but it actually happens. It's because there are these water spouts, which are kind of like tornadoes. Okay, they kind of sweep through bodies of water, and they suck up the fish along the way, and sometimes they suck up other aquatic organisms, and then they send them inland, and it appears to be raining from the sky, right? But actually, it's just a natural weather phenomena. But people in the past, they didn't really understand weather patterns, and they see this as again, support for the concept of spontaneous generation, life seemingly arising from non-living matter. So there was this guy, Francesco Redi. We're going back in times, okay? The first time someone tried to test this hypothesis was in the 1600s. There was this guy named Francesco Redi, and he wanted to test the theory of spontaneous generation to see whether it's true or not. And the way that he did it, the way he tested it, involves making observations, asking questions, and so on and so forth. And if that sounds familiar to you, that actually is the scientific method. Right? He actually is credited with being the first person to kind of come up with this scientific method and to use it to test whether a hypothesis is true or not. So the scientific method you should know by now, I hope you know by now, involves the first step involves making observations. And the observation he made was that flies and maggots can be seen around pieces of meat left out on the counter. Following observation, you have to ask questions. The question he asked was, where do flies come from? Is the rotting meat transformed into the flies? Now, once again, you might look at this and kind of laugh it off as like ridiculous. Why do we even have to do a scientific test to check this? Like, obviously, this is not true, right? But you gotta remember, this is hundreds of years ago, right? Things that are obvious to us now, things that are common knowledge to us now, is not necessarily so back then. I'm sure people in the future, like 200 years, 300 years in the future, look back at some of the things we do today, but they would probably laugh at us as well, right? Okay, so remember, this was in the past. It was a legitimate question for all intents and purposes. Okay, so he has to come up with a hypothesis. After you ask the question, you got to come up with a tentative answer, right? Okay, so this was the hypothesis he made. Only flies can make flies. Rotting meat cannot be transformed into flies. Right? This is a valid hypothesis because what are the two conditions we need to satisfy for a valid hypothesis? It needs to be what and what?
Testable and falsifiable.
That's right. It needs to be testable and it needs to be falsifiable, potentially wrong, right? And
Right.
this satisfies both of the situation, both of the conditions. All right, let's take more notes. I hope you have more paper. There we go. This is Radi's experiment. Francesco Radi. All right, so according to legend, this is what happened. He had 3 jars. 3 jars. Right. So that's the first jar. He has a second jar, and then he had a third jar right here. Okay. He put a piece of meat in it. Each of them. That's the meat. Another meat. And then another meat. In the first setup, there is no coverings. Okay, it's just exposed to the air. The second one has a netted cover. So like a mishmash. And then the third jar, it was sealed. Okay. Not sure what he used to seal it, but it was covered. Maybe he had a lid or something. I don't know. So that's the setup. I want to ask you a couple of questions here, and hopefully you have the answer for me. In this setup, what is the independent variable? What is the only thing that he changed between the groups? Very good. The type of covering. Oh, by the way, in case you guys think I'm like answering my own question and talking to myself, when I say very good, it's because someone answered in the chat. Okay, so just so you know, you might want to open up your chat box and see what other answers people are typing. Okay, yeah. So it's the type of covering being used. Okay, is it no covering, netted cover, or is it sealed? That would be the independent variable. Okay. How about the dependent variable? Dependent variable. What is he trying to observe? What is he trying to measure? He left these things outside for a week and then came back to it. What was he looking for? Okay, yeah, he's looking to what happened to the meat, but specifically,
Flies.
you know, I'm sorry, what's that?
Flies?
Flies, yeah, exactly, right? He's looking for the presence. Presence of flies and maggots. Okay. Now I'm gonna come back to this, but take a look at the hypothesis, right? The hypothesis was that only fly can make flies, and rotting meat cannot transform into flies, right? So he's looking for flies. He's looking for a presence of flies and maggots as well. All right, I'm gonna do another poll with you, but hold on, I gotta give you the question. Okay, this is A, this is B, and this is C. Which one is the control in this setup? Remember, in every experiment, you need to have a control to act as a reference to compare with. Which one is the control? And just a friendly reminder, the control is the one that you don't change anything to it, right? You just let it be. It's the default. Right, so which one is the control? Okay, so most of you got it right. This would be the control. This would be the control. Okay, you are not changing anything. You just have the jar with the meat in there, not adding anything to it. And then these would be the tested group, the treated group. You can say this is treated group 1 and then treated group 2. Okay. Now I am sure you you can predict the results. Okay. Again, like this should be common sense for us, right? Flies and maggots on the first one for sure. These are flies buzzing around, and then you got the maggots crawling around. Okay, if you don't believe this, try it yourself, and you will never forget it. What about B? Do you think there are maggots and flies in B? Little, yeah. Yeah. There will be, okay. So what he saw would be flies and maggots, but they're on the net. Okay, they're not in the meat itself, just like on the cover on the net. And here, no flies, no maggots, right? So based on this result, he accepted his hypothesis. He concluded that conclusion only flies can make fly. Or you can say he concluded that meat cannot be transformed into flies. Okay, so spontaneous generation is not true. Therefore, is not true. Because if it was, then you would see maggots and fly on the meat in the sealed jar. But you don't. So that's that. Okay. Now I'm just gonna talk through a bunch of standardized variable here. Okay. Other than the covering, everything else should be the same for this to be a valid experiment, right? So the meat he used would have to be the same meat, okay, same type of meat, same age of the meat, okay, all fresh, for example, from the market. They would have to be in the same area. You will leave all 3 jars in the same area, so they're exposed to the same kind of temperature, same kind of heat, same kind of humidity. Right? You would leave them out for the same amount of time, right? A whole week for all of them. You would use the same jar, just the lid is different. Right? So all these things are considered as standardized variable. All right. So let's take a quick break. We will continue at 1:35. I see you in a bit. All right, let's keep going. Now, you would expect something like that to be relatively convincing evidence that spontaneous generation is not true. Well, some people believed it. Some people agree that spontaneous generation is not true, but not everybody was convinced. Right? Some people argue that while spontaneous generation might not apply to things like flies and maggots, they still continue to believe it might be true for microorganisms, right? For bacteria and things that we cannot see with our naked eye. Right? So then the question was finally answered definitively in the late 1800s by this person. His name was Louis Pasteur. You might not have heard of him before, but he invented a process that is named after him and is still being used this day. And if you drink milk or if you consume honey, then you are benefiting from this process. Does anybody know what the process is? What am I referring to?
Pasteurization.
Exactly, pasteurization. Right? You can't
Sure.
just drink the milk raw from the animal, right? You're gonna get pretty ill, I'm pretty sure. Right? So like you gotta pasteurize it first. You have to basically kill off all the harmful bacteria and things like that. Okay, so you have him to thank. Anyway, I am gonna quickly show you his experiment. It's pretty straightforward. I'll keep it short. All right, so more notes. This is Pasteur's experiment. Pasteur's experiment. So he had two flasks, and the kind of flask he used is called a volumetric mass. It looks like this. Volumetric flask. It looks like this. So that's one of the flasks, and then he had another one, and this one has a special neck connected to it. Okay, like that. So this is called the open top flask. And because the neck here looks like a swan, this is called a swan neck flask. Okay. Then he filled the flask with some broth, like chicken broth, kind of broth. I mean, I don't know if it's chicken, but then like some kind of broth, okay? Like in case you don't know what a broth is, I'm saying it's like chicken broth or beef broth, what have you. So initially, he boiled both flasks to sterilize the broth. To sterilize means to kill off all the living things in there, right? So if there were microorganisms to begin with, well, now they're dead because you boiled them. Right? So that's part of standardizing the setup here. And then he left the flask outside for a couple of days, and he came back to look for microorganisms. Right? So in this setup, this would be the control, right? No special neck, and this would be the treated group. And so after some time, I don't know if it was a week, but after some time, only microbes were found in which flask do you think there will be microbes in the open top or in the swan neck?
Open top.
Yeah, in the open top flask. Very good. And we all know why, right? Because the microorganism from the air can like fall in and then start growing, right? That's why we put saran wrap on our food when we're not eating it, and we try to cover it with a lid or something, right? So that the airborne microbes not gonna land on the food and spoil them. So no microorganisms were found in the swan neck flask because even though there are airborne stuff, when they fall into the swan neck, they all get trapped here. There's no way for them to crawl up, right? So the broth remains sterile. And so he, using this experiment, he definitively showed that spontaneous generation is not true for big organism, and it's also not true for microorganism. Right? So we now know only life can give rise to more life. Right? We actually will learn that in lecture 3. And that's a characteristic of living things, right? They are able to reproduce, so they don't come from non-living things. And that's it. Any questions at all about any of these? Excellent. Let's do another poll question. Anyone else before I close the poll? Okay, so the independent variable, the one thing that he changed between the flask is the type of flask used. Is it open or is it swan neck, right? The type of broth used, that would be standardized variable. You want it to be the same kind of broth in both flasks. Whereas the presence of microorganism, that would be the dependent variable. Okay. This is also standardized. And the presence of flies, that's like the wrong experiment, right? That's Rady's experiment. It's nothing to do with Pasteur. All right. We don't have time to go through the whole thing here, but briefly on the internet, there are all sorts of claims on the internet, but there is this one claim that says, if you water your plants with microwave water in just 9 days, you're gonna kill the plant. Okay, so the person who's posting these pictures, they're like, see, the microwave is not good for you. If you microwave the water and it's able to kill the plant, then, imagine what it will do to your body when you eat microwave food. That's what they are claiming. Okay. Now, just to clarify, when they say water the plants with microwave water, they don't mean like straight out of microwave, okay? Because that's definitely gonna kill your plant. All right, like if it's like boiling hot and you pour it on your plant, you're gonna kill it for sure. This is like you microwave the water and then you let it sit until back to room temperature, and then you use it to water your plant, and it's gonna kill it in just 9 days. So throw away your microwave. That's what they say. I'm just curious. What do you guys think? Do you think this is true? There's some truth to this. If you think it's true, please choose A. If you think this is not true, please choose B. I am curious what you guys think. Okay, anyone else? This is very interesting. Anyone else want to chime in? Tell me what you think. Okay, almost every time I do this with any class, it's almost always 50-50. Okay, half the class thinks this is true, and the other half thinks this is not true. Okay, but this is something you can do an experiment to test on your own, right? Okay, don't believe what I tell you. Go figure it out yourself. But to keep you from, to keep you from guessing and then in suspense or whatnot, I'm just gonna tell you. Okay, this is absolutely not true. Right? This is absolutely not true. And there's nothing. You're not gonna change the water in any way when you microwave it. Okay, you microwave the water, heats it up, and then it cools it back down. It's the same water chemically as before you microwave it, and then you use it, you drink it, you use it on your plant. Nothing's gonna happen. Okay, if you don't believe me, that's fine. You try to do an experiment using the scientific method, and you will be able to see for yourself. Okay, so many things on the internet, along with this one, turns out to be not true. Okay, some of them we can try and figure it out ourselves. Others may be a little bit more difficult to verify, but it's always good to question what you receive. All right, we're gonna move on to the next thing, which is experimenting, experiments that involves human subjects. Okay, involves human testing. It's a lot more complicated when you involve humans in any kind of research. Unlike the plans where you can use the same plan for your experiment, no two individuals are exactly the same, right? Like unless you have an identical twin, and even identical twins are not the same in every single way, especially like as they start to grow up. There are many factors that could change them, right? So like no two individual humans are truly the same. So that makes it a little bit harder to standardize a testing. And moreover, we have to take into consideration of ethical guidelines when we are dealing with human subjects. You need to, for example, have their consent. Okay? They have to agree to participate in your experiment voluntarily. Okay? You cannot coerce them into doing it. You cannot force them into giving you their consent. And the consent needs to be ongoing. If they agree to participate at the beginning and then they change their mind halfway through the experiment, you have to let them go. Okay? There has to be reasonable measures that are taken to protect the people from both physical and mental harm. Okay? You cannot just test a new drug on them not knowing how much harm is going to cause, right? There has to be reasonable data from, say, animal testing that shows that it's relatively safe in animal before you can use it on humans. So there are a bunch of ethical guidelines that needs to be taken consideration. And in fact, anytime you do an experiment involving humans, you need to submit your proposal for ethical board to approve to see whether or not it adheres to the ethical guidelines that are created. And it's a little bit different for different countries, but generally it's surrounds the similar kind of things. Another thing that makes it complicated for humans is another thing that's complicated involving humans is that humans have bias sometimes. Okay, there are bias that you might be aware of yourself, and then there are also like psychological biases that you're not consciously aware of, and those things can actually skewer the results. It could change the result and make it less accurate. And so to adjust for these biases, whenever we deal with human subjects, we need to include a placebo. Okay? The placebo becomes our control. It becomes our baseline. So what is a placebo? A placebo is a sham treatment. Sham treatment means it's not real. In the case of testing like a new drug, a placebo might be a substance that has no known effect on the outcome that you are trying to test for. Okay, some people call it a sugar pill. Right? It's just candy. It's not supposed to do anything to treat a disease. Okay, so we use that as a placebo. Right? In setting up an experimental group, I'm not going to give you another note. Okay, I'm just going to verbally tell you this should be quite simple. Right? Let's say I test for the effectiveness of a new vaccine, then you would have two groups. Okay, one group would have people receiving the actual vaccine, and then you would have another group that's receiving the placebo. You're still giving them a shot. Is a little bit different from the control where they receive nothing. For placebo group, you're actually giving them a blank shot. Right? So the placebo vaccine is going to have all the same ingredient as the actual vaccine minus the active ingredient. Okay, during the pandemic, many people receive what's called the mRNA vaccine. If you don't know what an mRNA is, that's okay. We'll learn that later in the course, but that's the active ingredient. So people who receive the placebo will have the same ingredients, they're all the same solvent, the same preservative, and everything as the actual vaccine, but it will not have the mRNA in it. It doesn't have the active ingredient. Okay, so that's what a placebo is. It's a sham treatment. Now, let's take a look at an example of where placebo is used outside of the context of an experiment. So there is this birth control product called Freya 28. It's basically a contraception. If you don't want to get pregnant, you can take this contraception, and the package comes with 4 rows of pills, 3 rows of white pills, which are the contraceptive, and then you have 1 row of green pills, which are placebo. These green pills do absolutely nothing for you. Okay, they are just blank pills, and it's included in the package for 1 week. Now, can anybody guess why am I paying for the full price and getting 1 week of placebo? What's the purpose of including the placebo there? Ideas? No? Okay. So when the person is on the contraceptive, they are not having the menstrual cycle, right? It actually prevents the ovulation from happening. But you know, when people choose to go off the pill, then they would have their a period during the 4th week here. And during that time, right, you are encouraged to take the blank pill to help you keep track of time. Right? Someone said routine, and that's exactly what it is, right? You continue to take the pills, and then when you run out of pills, you know it's time to open a new pack and start the next cycle of contraceptive, right? So it's just a time tracking mechanism, right? It's better than you tracking it yourself, because sometimes we go on with our busy lives and then we lose track of time, and then you're like, oh, am I supposed to go back on the pill like today or tomorrow, or like is it 2 days later, right? But by having the placebo in the package, it helps you keep track of time. That's all it is, okay? So why is this an interesting story? Well, it's an interesting story because the company kind of messed up 1 year. Okay, this was over 10 years ago, okay? But still, it's worth talking about. There was a lot of the pills where they made a mistake and they switched the placebo pills with the actual pills. Right? So if you purchase that a lot, you would have 3 weeks of blanks and 1 week of contraceptive, right? And you can imagine what kind of problem that could cause, right? Especially if you're not used to the product and you didn't know that the green pills were like, you know, the placebo, and then you thought they were just normal, and you would just be taking the green pills for 3 weeks thinking you are on contraception while you're not, right? The result could be undesirable, right? So once the company found that out, they issue an emergency recall, and people were advised to use backup contraception immediately. Okay, so that's an example of how placebo is used outside of the context of an experiment. Now, when you do an experiment with humans, sometimes people do what's called a blind experiment. In a blind experiment, the subjects, the people who are being tested on, they don't know what kind of treatment they are receiving. So that will help minimize the bias in the subjects, in the person. Okay. Now, sometimes like minimizing the bias is not as important as other cases. Okay. If you're testing the efficacy of like a new vaccine, then the placebo is not so much to minimize the bias. It's more for creating a baseline to compare with, because there is nothing to be biased about when it comes to receiving the vaccine. What I mean by that is you cannot say you cannot have a psychological effect where you feel like you are more protected as a result of the vaccine, and therefore you don't get sick as often. Like, you cannot will yourself into not getting sick, right? So it's not really for minimizing bias in that case. I will give you another example though. Like, if I create like sleeping pill, like a new sleeping pill, right? And I want to test like how good it is, right? Then the placebo would be to minimize psychological effect, because when you take a sleeping pill, there is a certain degree where if I think I'm taking something that will help me sleep better, then you will end up sleeping better. Right? It's true for some people. Some people, if they go to bed thinking, "Oh, I'm gonna have another bad night of sleep," then it turns out they have a bad night of sleep. Right? It's almost like a self-fulfilling prophecy, right? So if you're testing a medication that involves those kind of issues, then the placebo is needed to minimize psychological effect. Okay, but like if you're testing a new drug on like cancer or something like that, right? Then the placebo is not for minimizing the psychological effect, right? It's just for establishing like a baseline, right? Because in those situations, no matter what your psychology is, or no matter what your bias is, no matter what you think, thinking about it is not going to change the result, right? Does that make any sense? Anybody have any follow-up question? I might have made it sound more confusing than it needs to be. Okay. Double-blind experiment. In a double-blind experiment, both the subject, the person who is receiving the test, does not know what they're receiving, and the person who is giving the shots also don't know what they're giving. Okay, so both of them don't know. Right? And it is some third party that has the data that match who received what. They would know who's receiving what, and they would be the one who's analyzing the results. And that way, we can minimize bias in both the scientists as well as the subjects. Because sometimes there are conflicts of interest. Right? If the scientist works for like a pharmaceutical company, they have an invested interest in having the product work, right? So they could sell it for a profit. And so when they evaluate the results, they might not be as critical as they should have been. Right? So by doing a double-blind experiment, we would minimize those kind of undesirable outcomes. Okay, so the gold standard in doing experiment is the double-blind experiment. All right, let's say I have a new product called Sleep, and I want to know if this drug is going to help reduce the symptoms of jet lag. Jet lag is what you get when you go from like one time zone to another time zone. Again, like you can't sleep, you get headaches, you are like, lose your appetite and whatnot. Some people are not affected by it. Okay, others are more affected by it. So I want to know if my new drug is going to help relieve the symptoms of jet lag. So I have two groups here. I have the control group, which is receiving the placebo. I am not telling them that they are receiving the placebo. I'm just giving them a blank pill. Right? They don't know it's a blank pill. They take it, and then later I ask them, how was your jet lag? Right? 80% of the people say they experience symptoms of jet lag. If I give them the actual pill, again, I'm not telling them that they are receiving the actual pill, but I give them the actual thing, and then I ask them, how was your jet lag? Right? Only 30% of the people reported symptoms of jet lag. So based on this result, do you think the new drug is effective in reducing the symptoms of jet lag? If you think it's effective, please choose A. If you think it's ineffective, please choose B. And if you think it's inconclusive, please choose C. What do you think? Okay, it looks like we have a lot of undecided folks here, but that's okay. Let me walk you through it. Maybe it will make more sense after I explain it. Look, what's the placebo? Placebo is just a sugar pill, right? It's nothing. It's a blank. It doesn't have any medical effects on anything. It's just a blank pill, a sham pill, a fake pill. Do you expect a fake pill to help you with your jet lag? Obviously not, right? Like if it's not supposed to do anything, then it's not supposed to have any effect on your jet lag, right? So that's what we see, right? All 80% of people still report symptoms of jet lag. Okay. You might ask, well, I mean, like it's not 100%, so that means maybe it helped 20% of the people. But you gotta understand, jet lag doesn't affect everybody, right? I told you at the beginning. Some people are just naturally not gonna be bothered by the change in time zone. So maybe those are the 20% people. Okay. Treatment group. Right? These are the people who receive the experimental drug, and only 30% of them report jet lag. Okay, so compared to the control, compared to the fake pill, compared to the placebo, we see quite a bit of reduction, right? In fact, it dropped from 80% to 30%. So that's a quite significant drop. Right? So based on this, we can say the drug is effective. Okay, it's helping with the jet lag, basically. Now over here, if this was the result instead, do you think is effective or not effective? Now you can just think about it in your head, and then I'll tell you what it is. Right, so in this case, if you give them the sugar pill, it helped them sleep better. It helped them have less jet lag symptoms. Okay, but that's not supposed to happen. The sugar pill is not supposed to have any effect. Yet you give it to them and then they experience symptoms reduction. Same thing with my pill, right? The new drug. It also helped them reduce symptoms. So if you give them candy, the placebo, right? If you give them candy versus you give them the actual medication and it achieves the same outcome, then is the drug working? It's not, right? Yeah, like
Yep.
if the candy performs as well as the drug, then I might as well take the candy, right? You know what I mean? Right? So if this was the result, it would suggest to you that jet lag is more of a psychological problem, right? It's like just in your mind, okay? So if you give them something, tell them it will help, it turns out helping them, right? Because they believed in it, okay? It doesn't help everybody, right? But it helps a majority of the people. Does that make sense? Right? So in this situation, that's why we need to have the placebo, right? To minimize the effect. Okay? Even though we still call it a placebo in testing like a cancer drug or something, but the point of including it is quite different. Okay, like again, you cannot will yourself into getting rid of cancer, right? So any psychological effect would be irrelevant, so to speak. All right, another exciting concept check question here. We're almost done, guys. Hang in there. Just have like 4 more slides. All right, that was a minute and a half. Thank you for those of you who have participated. Let's take a closer look at this question. We are testing the a drug that's dissolved in saline in pregnant mice. So the control would not involve male mice. Right? So anything that has male in it's not going to be the answer. And also we are testing this on pregnant mice. So non-pregnant mice would also be out of the question. Now, do we for the control group, for the placebo, control and placebo are sometimes used interchangeably, right? For the control group, do we give them more drugs or do we only give them saline? Well, if you remember, the control group is not supposed to have any active ingredient, right? So the correct answer would be E. Okay. I hope that makes sense. All right. In the last couple slides, I'm just going to talk about how we can use what we learned from this lecture to evaluate different resources, different things that we see on the internet, right? Like things that you see in your feeds or things that you need to research to do reports for other courses, right? How we can use what we've learned from this class to evaluate the accuracy, right, of some of these sources. In many situations, people are able to identify correlations between two variables. A correlation just means you see some kind of trend between two things. Okay, if one goes up, the other goes up. That's a correlation. If one goes up, the other goes down. That's also a correlation. Okay, so there's some kind of relationship between two things. According to this graph, if a person is more stressed out, then they have a higher chance of catching a cold. That's a correlation. Okay? Having a correlation is fine, but a lot of people jump to conclusion that if you see a correlation between two things, then one must cause the other. But that's not true. Correlation does not necessarily equal to causality. Causality means A causes B. If A happens, B will happen for certain. That's causality, right? So correlation does not imply causality. There are many reasons why a person might be very stressed out. They might have other illnesses, they might have poor diet, little exercise, or little sleep, all of which can contribute to being stressed out. All of which also can contribute to being more prone to getting cold, right? So just because high stress seems to increase the frequency of cold does not mean there is a direct cause between the two things. Maybe it's something else that's underlying that's causing the cold frequency or causing the high stress situation. So we must not take things at face value. Now, let me, there is a website here. You can check it out yourself. I think the link still works. Okay, you can try it out. It gives you all sorts of random stuff that have very close correlation with one another, but doesn't absolutely have nothing to do with one another. For example, in the red graph here, it is per capita cheese consumption, how much cheese people eat basically in a country. And then black line is the number of people who die by becoming tangled in their bed sheets. Apparently that happens. So there is a correlation of 94.71%. That's actually really, really high. Okay? So you can see the two lines are very close to each other. But I can say with pretty high degree of confidence that eating more cheese is not going to make you more prone to getting tangled by your bed sheets. Right? One thing has absolutely nothing to do with the other, and yet they are closely correlated. Right? So this is a perfect example where correlation does not imply causality. Okay? If you go to the website, and there are a bunch of other random ones that you can see. So here's the thing. If you have a huge collection of data, okay, just by chance, some of these data will have a correlation. That's just how statistics work. If you have a big enough sample, you are likely to see some kind of relationship between some of these variables, just purely by chance, nothing else. Okay, and that's what we have to remember when we see headlines like these. Okay, so I did a random search about coffee consumption. Okay, I used to drink a lot of coffee. I don't anymore. And some people say coffee is good for you. Some people say coffee is bad for you. If you do a Google search, Google News search, you will see conflicting articles. For example, you will see drinking more coffee might reverse liver damage from booze. Right? So that's like a good thing, right? It seems like, and people who drink coffee look at that, it would be confirming their beliefs, and they're like, "Yeah, I knew it. I knew drinking coffee was good." And then they share it with their friends. And then over here, we have another one that says coffee consumption in either parent may raise miscarriage risks. Right? And then that tells you drinking coffee is not so good, right? Right? And then there are other ones that would prevent colon cancer, cut your risk of developing endometrial cancer, right? So like there is these conflicting information. And what you must remember again is if you have a big enough data set, let's say I have coffee drinking in one column, and then I have a column about liver damage, I have a column about miscarriage, I have a column about colon cancer, a column about graduating from college, a column about having how many kids you have, right? Like if you have a big enough data set, some of these things are bound to have some sort of relationship from it. Okay, and so we must be careful when we see these headlines, right? We must use the scientific method to understand, to see whether or not these are just correlation or are they good science, right? Especially nowadays, right? There are a lot of clickbaits. People just want you to share information, and people lack critical thinking skills. They look at something like this, they rarely click into it and then find out the actual study. I mean, I didn't look into this, right? But like if I wanted to, we could, right? We can find out when this study was done. We can find out if it follows the standard of scientific method, right? Was it a double-blind experiment? Was it done with a big enough sample size? More importantly, who funded the research? Right? You got to understand a lot of times some of these studies are funded by big industries that have an invested interest in the outcome. I'm just saying, right? Like maybe this one was funded by, the coffee people and the alcohol association, right? Oh, let's come up with a study like this so we can boost sales, right? You can party all night, drink all you want on Saturday, and then Sunday you can buy the coffee to kind of cleanse yourself, right? Wouldn't that boost sales, right? So you have to understand who's funding these research and whether or not it is a believable science. So when you do your research for other courses, you often have to cite your sources, and you have to understand the difference between primary sources and the secondary sources. Primary sources are the original documents or original research. More often, these are they tend to be more accurate. They tend to have less bias. For example, academic research journals. In order to publish your result in a scientific journal, it needs to first be reviewed by other experts in the field, right, to make sure that you actually do the experiment in accordance to the standard that it needs to be, right? So they tend to be more accurate. Does that mean, there are no errors in them? Not necessarily. People have been caught faking data, fabricating results, right? That happens. But generally speaking, these tends to be more reliable. Okay? Interviews is another example of primary sources, right? Even fictions, things like that. As long as it's done by the person who created it, then it's primary source. Secondary sources are more like summaries and interpretation of primary sources, and that includes things like encyclopedia, even textbooks, right? Textbooks tend to be pretty reliable when it comes to like factual stuff, but if you read a textbook on history, then you gotta evaluate the source, because there's a phrase that says there's always two sides of the history, right? So it depends what perspective it's written in, right? You might only be getting one side of the story. Okay, so when we look at the sources, it's important to try to use some of the things we've learned and to evaluate whether it's good source or not. Okay, so hopefully you'll be able to use this in some of your other courses. You don't have to write any reports for my course other than the lab reports. You probably won't have to use any of these things for my stuff, but maybe in some of your courses it'll be important. And that's it for the first lecture. Okay. So for next class, which would be Wednesday, you will have to print lecture 2 notes. So if you go to the lecture 2 folder, there are the lecture notes. You can get the PowerPoint and the study guide. And don't forget, there is the study guide answer that I posted for lecture 1. Okay, start studying for the test, of course. And there will be class notes. That's the notes from last time, and I'll post the notes from today as well. Okay, thank you for coming, and I'll see you all on Wednesday. Have a good afternoon. Bye-bye.
Professor, before I leave, can I
Sure.
ask, do we have any assignment due or quizzes for this week?
No, nothing. If you want to know what's going on when they're happening, you can get the under the useful information. There's a weekly schedule. Okay.
Good. Okay, thank you.
Yeah. So there it is. Okay, our first quiz is September 23rd.
Okay, thank you.
No problem.
Have a good day. Bye.
You as well.